A very warm welcome to all of you. Welcome to our live phone-in program of CIT and CRT. Today our topic of discussion is matter in our surrounding. It is based on class 9th NCERT textbook. And we have Professor R.K. Parashar and Professor Anjini Kaul with us, who are professor in Department of Education and Science and Mathematics, NCERT. We welcome you, ma'am. We welcome you, sir. Thank you. First I'd like to ask you, ma'am, what exactly is matter? How do we define it?
Okay, see, if you look around, you see number of things.
Right.
And all these things, they have different shape, size and texture. So all these things, they are made up of some material, and scientists have given name, they have called them as matter.
Right.
So matter is something which occupies space and has mass. For example, the clothes which I am wearing, the paper which is lying on this table, for example, we have beaker here,
right.
Or if you go out, you can see trees around,
right.
And water which we drink, air which we breathe, all these things are matter. And basically scientists have discussed matter on the basis of their physical properties and chemical nature. So this is what we call matter as.
So sir, we say that matter is made up of particles. Can you please elaborate this?
Yeah, some matter seems to be continuous in nature if you see the block of wood or is this stone, but it is actually made up of small particles. We can prove by seeing by doing one activity in which we can take one spoon of either salt and sugar, and when we dissolve this into a glass of water, when we stir, what we observe, whether the volume of that liquid will increase or it will remain same. Basically, the volume remains same. The solid substance like sugar or salt have a small particles. They dissolve in that and they occupy a space between the particles of the water. So by this activity we can prove that the matter is composed of small particles which spread in the water and occupy the intermolecular spaces of water.
So I would like to inform our viewers who are watching this show that they can call on our toll-free number. If they have any suggestion or any query, our number is 1800-111-265. Another number is 1800-112199. So we are talking about matter. Ma'am, can you please tell us that how small are these particles of matter?
See, as Professor Parashar said, metals are made up of very small particles.
Right.
You cannot even imagine how small are these particles.
Right.
For this, let us show a video where viewers can understand how small are these. So, please play the video.
Sure.
See, here you can see that we have taken number of containers. Okay, in each container, if you see that there is, we have not put, okay, now they are showing it. Okay, in the first beaker we have put a few crystals of potassium permanganate. Okay, now if we add water in this, what will happen? Obviously, we'll get some colored solution. Okay, so when after stirring, you can see that the color is showing uniform color in the entire container. Now, if we take few ml of this solution and we transfer it into the another beaker, that's what we are showing in this video. See, we have taken 10 ml of this solution and we are going to dilute it with water. So, because we want to keep volume same in all the containers. So now we are adding water. And see, we are going to make up solution. We are showing it somewhere in this on the screen that it is going to be 40 ml. We can see it here. So again, you can see the solution is colored. Now you can compare the color of the two beaker in the first beaker and the second beaker. Okay, now we are transferring from the second beaker into the third beaker. Again, we have taken 10 ml of this solution and we are going to dilute again and we are going to make up the volume similar as with what we have done in the earlier beaker.
Right.
So see, again we are pouring and we are going to put it up to 40 ml. Now see the color change. Okay,
The
can you
color
make
is
out?
getting
Yes,
lighter and lighter.
yes. So it's getting lighter and lighter, and Now again, this we have done maybe 4 times or 5 times. We can do it maybe 10 times and 20 times. So somewhere or the other you will see this color after so many dilutions. So this shows that the particles are so small that even after so many dilutions, we can see that color. Maybe a stage will come, if we'll do it maybe 50-40 times, that we will not be able to see any color. So this shows that how small is the particles of KMnO4. This means that's what I said, we cannot even imagine how small are these particles. It's like, suppose you take a piece of paper, for example, and you tear it, and you keep on tearing that piece of paper. A stage will reach when you will not be able to tear it further. Fine. So I can say that small particle of that paper I can see. But if we put all these small bits of paper, children can do that. They can tear the piece of paper and see the small, piece of paper somewhere and case that this is the smallest particle in this particular activity. But if we put all these particles of paper together, we can at least see that, something we can see which will be very concrete and one can see. So this activity and, the one I am saying that you can use paper, we can say that particles, they are very small, and I'm repeating that one cannot even imagine how small they are.
I can also add up to this. See, when we take a salt into the water, its volume doesn't change. If you take a pebbles in the same glass of water, you see there is a change in volume because the pebble size is bigger, so the volume of water will increase. But when we take a 1 or 2 spoon sugar or salt into the water, there is no change of the volume. So it itself proves that the particles of the matter, they are very, very small in size.
So are these particles continuously moving?
Yeah, we can have a daily life experience when a unlit incense stick is there. There is no smell in the room. Okay, when we lit the incense stick, you will see after some time beautiful fragrance is all over in the room. Another activity also one can see that when we put a drop of a ink in a glass of water, see after some time it gets spreaded throughout the liquid. It proves that the particles of the matters are always in the motion.
Ma'am, I would like to ask you, will there be any change in the movement of particles with the change in temperature?
Yeah, it's a good question. As Professor Parashar said that particles, they are always in motion, whether it's solid, liquid or gas. But then when you change the temperature, the motion increases because these particles, they gain energy. They gain that. Because of motion, they gain that kinetic energy, and when they gain this kinetic energy, you can see that motion of the particles will be little faster. So for this again, we can show a video where, can you please play the video?
Sure.
So in this particular video, we have kept 2 glasses, both of them half filled with water. You can see in the first glass, I mean the performer, she's going to put this KMnO4 crystals again in this first beaker. In this particular glass, we have cold water. We have placed cold water. Okay. And in the second glass, we have put warm water. Now you can ask me, how can I say this is warm water? You can see those, steam somewhere at the mouth of that glass. So the moment we put that KMnO4 of equal quantity in both the glasses having equal volume of water, you see the one which is warm, you can see the warm water, that see the diffusion is very fast. See how particles are moving, and you can see the uniform color solution. Throughout the solution you can see that uniform color. But in the initial one, that was the cold water, it takes little longer. So we say that when we increase the temperature, the motion of the particles increases, and easily we can make out that temperature, it helps in the movement of particles.
So Dr. Parashar, how can we make the students understand that particles of matter attract each other?
See, we can prove this by again taking a simple activity. See, the water is there inside this petri dish. Okay. Can we cut this water?
Okay, let me try it with that pencil. We cannot.
Can we cut the stream of water coming from the tap?
No, we cannot.
No, we cannot.
So this proves that the matter particles, they attract each other, and it seems they are in the continuation.
Okay. Okay. Now, Dr. Anjini, can you please discuss about the states of matter? Like, what are the different states of matter?
Okay, so far we have talked about matter. We have talked about particle nature of matter.
Right.
We have talked about that temperature affects the motion of the particles. Now, it's states of matter. Yes. In this particular class, for example, for class 9th, we say that there are 3 states of matter. One is solid, the other is liquid, and the third one are gases. Now, for example, if I say solid, so for this solid, if I take, for example, this stone, okay, this stone, I say this is solid. How can I say this is solid? Because if I press it, it's very difficult for me to press it. I mean, hardly I can press it.
Right.
And any solid of that matter, if I put this pencil also. So it's very difficult to press this pencil also. And for example, if I take this stone and maybe I'll make a boundary of this stone, okay, by using this pencil or pen. You know, students can do this at home. They can take various, types of solids, and then can draw, boundary. And
Right.
if I see this, it has a uniform shape.
Right.
Now, for example, I say that this pencil, if I see this pencil, it looks straight.
Right.
And if I take this beaker and I place this pencil in this beaker, will I change the shape of the pencil? No. Okay, so we say that solids, they are rigid because we cannot press them. They have a certain shape, we cannot change its shape also. So they have the arrangement of particles, we say in solids is uniform.
Right.
Okay, but there are examples. Suppose I have this rubber band, and if I stretch it,
Right.
fine, I can change its shape,
Right.
isn't it? And I can if I stretch it longer, it can break.
Right.
But then still we say this is solid because it can regain its shape back.
Okay.
Fine. Similarly, if students, they have sponge at home, they can take the sponge
Right.
and see, a sponge has a fixed shape. It can be rectangular, it can be triangular, it can be anything.
Right.
And they can draw its boundary, everything can be done. But then if we press the sponge, sponge can be pressed.
Right.
And then if we leave that force which we are applying on it, the sponge can regain its shape.
Right.
Okay, but then why we can press it? Because in sponge you can see various pores, and the air which is there in the atmosphere, it gets trapped into those pores. When we press the sponge, the air escapes. Fine, and when we leave it, the pores, they get that air back.
Okay.
So they can regain that shape. These are all, students can ask, because I said that solids are something very rigid and we cannot press them. And if I talk about liquids, they are fluid. For example, if I take this water in this petri dish, okay, then liquid, it has attained the shape of the container.
Right.
Fine. If similar liquid, if I put it in a beaker, see, if I put it in a beaker, what will happen?
It has
Now
taken
this liquid has again taken the shape of the beaker.
Right.
So we say that liquid are fluid. So so I have talked about solids, I have talked about liquids.
We can say that liquids do not have a fixed shape. It takes the shape of the beaker or
the
whatever
container, they are fluid.
Right.
Their particles, they are not arranged in that order as compared to solids.
Right. So now the third state of matter, that is the gaseous state. Sir, can you please elaborate on that?
The third state is the gaseous state.
Right.
Again, the gaseous state is also a fluid. But what is the difference between the liquid and gas is that the volume of liquid state remains fixed. When you pour from one pot to another pot.
Right.
But in the gaseous state, it acquires the volume of the container itself. And you see in the liquid or a solid, you can see its surface. It has a surface, but in the gaseous state, there is no surface. It occupies all the space available in the container.
Right.
And the difference is also there in the property of compressibility. The liquids are not compressible, solids are also not compressible, but gas can be compressed up to certain extent. We can show by doing this activity. See what is there inside the syringe. See,
Gas.
there is a air,
Yeah.
and air is an example of gas. See, I am just trying to compress it. See, it is getting
Compressed.
see, on application of force, it is getting compressed.
Right.
When I am releasing the force, see again
It's coming back. To
coming back.
the position.
So, Professor Anjini,
Yeah.
can also show this with the liquid, whether the liquids are also
Right.
Okay.
Right.
compressible or not.
Okay. If we take little water in this petri dish, fine, and this is this syringe, as he said that, see, if we say that there's nothing in this syringe, this does not mean that it is empty. There's some air is there.
Right.
So as he did, he just pressed it and we could easily press it. Now if I put it in, as I have taken liquid in water in this petri dish, if I pull some water, okay, and I put a finger on its nozzle, and if I press it, see, I won't be able to press this.
Right.
In case of air, we could,
Yes.
but when we have liquid, that is water here, it's difficult to press.
Right.
So that is what Professor Parashar was trying to.
So we can actually say that
Say.
liquids are not compressible,
Yeah.
right?
Yeah.
Whereas gaseous state are. Okay, so far we have talked about matter. So can matter change its state?
Oh yes. See, we all know when you take out, ice from your refrigerator, all children, they have done this. They take out this ice and put it somewhere in the room temperature.
Right.
It gets
Melted.
melted. So that is because of the temperature. See, when you put it somewhere outside, the particles, they gain that energy. The movement gets faster,
Right.
and solids, they starts melting. And the one thing which is very important here is that usually we measure, we say that melting point, when the ice melts, we say that melting point of ice is something like 0 degree centigrade.
Right.
Okay. But then in SI units, usually we say that it is 273.15 K. Okay. So in this class, particularly in class 9th, we have talked about the units, about this temperature. So little bit I would like to add here. Suppose we have to ask children, convert centigrade into Kelvin scale. So here we have taken an example of body temperature. We are saying that body temperature is 37 degrees centigrade. So to convert it into Kelvin, you have to add 273.15. But for the easy to get equations or mathematics easy, we have taken a we don't say 273.15. We take a roundabout figure, and when we add 273, and we say that 310.15 K. So we say that the body temperature is either 37 degrees centigrade or 310.15 K, or we can say 310 Kelvin. So, but in SI units, that which is internationally known, so usually we talk in Kelvin.
Okay.
So similarly, one more example, we are talking about acetone. We have written that is around 56 degrees centigrade, and if you convert it into Kelvin, you have to add this. And it can be other way around. If you have to convert from Kelvin to centigrade, then you have to subtract
the
it.
number. Right.
So this is what I wanted to talk about the units here.
Right, right. So isn't it surprising when solid melts, its temperature remain the same? And why is it so? Where does the heat energy go? You would like to
See,
yeah, sure.
yeah, it is called hidden heat. Basically, what happens, as just now Professor Anjini has explained, that the ice is converted into the liquid at room temperature. See what happens basically when there is a transition of state, like from the solid state to liquid state. See, the molecules absorb little energy just to convert its state. Otherwise, what happens if we take a plain water and supply heat and measure the temperature? As you heat, the temperature of water increases. Okay, all of the heat is taken to increase the temperature of the volume or whatever is the matter. But whenever there is a transition of state, this energy is taken to convert the physical state from liquid to solid or from liquid to gas. So at this junction, the energy is utilized to convert this state, not utilized for increasing the temperature. That's why it is called hidden heat or the latent heat.
Okay, so well, I would like to add here, Professor Parashar has very nicely explained as latent heat, which is called as hidden heat. I would like you to please play this video, which explains things beautifully. So, see here we have, there's a setup of experiment. What we have done, we have shown in this particular thermometer a temperature which is room temperature, around, we have taken this video little, maybe in summer somewhere, it's showing 30 degree or so somewhere. Okay, now what you're watching on the screen is that we have kept this thermometer in the ice. So when we have put this thermometer in the ice, you could see that it is showing 0 degree centigrade. We can see it again here. And when we are supplying heat to this beaker in which we have put ice, you will see that there will not be any change in the temperature which we can measure from the thermometer, because you see the ice is getting melted. The moment the entire ice will melt, only then the raise in temperature will be seen in this video. See now, it was initially at 0, now gradually it is going, see up to 30 and so. So this shows that, as Professor Parashar said, it's a hidden energy. Now when we are, now the ice is already melted. Now when we are supplying further energy, this is going, now water is going to boil. So you will not find, see, water has started boiling, but the temperature is still remaining close by. Now you can see entire water, it's a bulk phenomena. When entire water is boiling, you can see the temperature is going near about 100. It's showing little higher because the water is not that pure. So we can say that as Professor Parashar said, it's a hidden energy. So it's somewhere in the in the content itself. Once the entire ice melts, only then we could find the temperature.
So like here we saw that there was ice cubes, and then it gets further heated, it gets converted into the liquid state and then into the gaseous state. Can we skip this part, like can solid state directly be changed into the gaseous state and vice versa? Is it possible?
Yes. When we say that solid, anything solid which goes directly to vapor phase without going through liquid state, that we call it as sublimation. Again, I would like you to show some video, because see, in science we don't believe in simply listening, we believe in doing. So since we don't have enough of time here, we cannot perform all the activities, so we would like viewers to watch these videos. Here you see we have taken this china dish. In the china dish we have put some camphor. Okay. Now after putting camphor, we are giving some heat. We are supplying some heat by igniting the burner, and the conical funnel is placed inverted on the china dish. Remember that the stem of the conical funnel, why I am saying these small things, because children may try these at in their schools. So when you place this inverted funnel on this china dish, you have to close the stem of the funnel with some cotton plug. Okay, when we are heating, giving heat, you will see that the solid which we have taken in china dish, it changes its form in the vapor state, and the moment it touches the surface of the conical funnel, because it is the surface of the conical funnel, the moment it touches it, it gets converted into solid. So we are not finding any liquid state here. See, very beautifully you can see the crystals here.
Right.
We have heated the thing in the china dish, for example camphor, and now you can see those crystals somewhere on the funnel. So once the experiment is over, you have to wait for some time. Remember, please don't burn your hand, children. You have to let it cool. In this video you have given enough time to get it cool, to get cool, and now you take this funnel and see these beautiful crystals.
Right.
We have not seen any liquid there. So this is conversion of something solid directly to a vapor state is sublimation, and then getting from that vapor back to the solid state
Right.
is called deposition.
Right.
Okay, these are the two things which we have shown in this video.
Right.
Would Dr. Parashar would like to add anything over here?
Yeah.
See, we have our daily life experiences when we put a naphthalene balls in our woolen cloth.
True.
What happens after 2-3 months? Whether we get those balls intact or
It evaporates.
To disappear.
Yeah.
so this is a phenomena of sublimation in which a solid substance gets converted into the vapor state directly.
So, Professor, do you think that increase or decrease in pressure can change the state of the matter?
Yeah, one can change the state of matter by adjusting pressure and temperature. See, like we have seen the ice, when it gets heated up, it converts into the liquid state, and when we supply heat to this liquid water, it gets converted into the steam.
Yeah.
So but see here there is a one point to note that merely changing the temperature is not sufficient to change the state. Pressure also plays an important role, and temperature. So by adjusting temperature and pressure, one can change the state of matter.
Okay. Professor Anjini, I would like to ask you, like often in my childhood I had observed that when we leave water in open and without covering it, it gets disappeared after some days. Why does it happen?
Yeah, that phenomena which you are talking about, we call it as evaporation. See, when we keep anything, any liquid, or for example I say water, when it is left open, so you will find that after some time, particularly during summers, you will find that water evaporates.
Right.
So what happens that since we have not talked about atoms and molecules, because we are discussing about particles, so I'll keep my discussion on these particles
Right,
also,
right.
only on this. So the particles which are there on the surface of the water,
Right.
they are already in motion. Fine. When they get heat from the surroundings, they start getting escaped. So the moment they escape, go to they usually escape, and you will find there somewhere in the atmosphere.
Right.
So this is how the evaporation takes place.
Right. So what are the factors that affects evaporation?
Okay. So basically, the larger the surface area. If we have a larger surface area, well, I would like to show it to my viewers that. What are the factors which are responsible? First of all, this is if we have a larger surface area.
Right.
Fine. The larger the surface area, children can perform this activity at home. They can keep little water. I'll quickly talk about this because I think we are running short of time.
Exactly.
So if we have little beaker with us with the water in a container,
right.
and we place water in a huge container where we have this, the surface area is more. Obviously, the motion of more particles will be exposed, so the evaporation will be faster. Similarly, increase in temperature, as we have already discussed. The more the temperature is, the faster will be the movement of the particles, and they will escape.
Right.
Humidity, rainy days, you will find clothes not getting dried up quickly because of that humidity. Because see, our atmosphere has limited amount of water it can retain. So if you have more humidity, the evaporation will be less.
Right.
Okay. Then similarly, wind speed. The day you will find that windy atmosphere, clothes will be getting dried faster. So all these factors, surface area, temperature, humidity, wind, this will all affect the evaporation.
Right. Thank you so much. We would have actually loved to continue this topic further, but we are running short of time, so we have to finish it right here. Thank you so much, viewers, for being with us. Our today's topic of discussion was matter in our surrounding, and our experts were Professor Anjini Kaul and Professor R.K. Parashar. Thank you so much for being with us. We will see you on Monday with another expert and another topic. Thank you so much.
Thank you.